It's almost surreal to consider that just one company has, well, fundamentally changed how our computers even work.
And not just change things, but become one of the most valuable companies on Earth.
Exactly. We are talking about NVIDIA, of course, and the man behind it, Jensen Huang. I mean, just think about that for a second.
Yeah.
One person's vision shaping everything from, AI breakthroughs to gaming, even self-driving cars.
The scale of it
Yeah.
is, it's just staggering, really. It's not just small steps. It feels like
Yeah.
a whole rewiring of computing.
And so fast.
Unbelievably fast.
Right. And that's exactly what we're digging into today. We've gone through a really insightful interview with Jensen Huang from Clear Abrams' YouTube channel, actually, to pull out the key stuff for you.
Yeah, we're skipping the usual earnings calls and management speak.
Exactly. We want the how and the why. How did NVIDIA get here? Was Huang thinking about what comes next?
So our mission for you today is pretty simple. Get the core insights behind this huge shift in computing, understand what's happening right now because of it, and then look at Huang's vision, especially around AI and robotics.
And the interview itself helps because it really focuses on those big tech shifts, the thinking behind the strategy, right?
Precisely. Less about the day-to-day finances, more about the foundational ideas.
Okay, so let's start at the beginning. Back in the early 90s, game developers wanted better graphics, more realism.
But the hardware just wasn't there. It couldn't crunch the numbers fast enough.
So where does NVIDIA come in? What was the big idea?
The key observation, as Huang tells it, was that in almost any software, it's a tiny bit of the code doing most of the heavy lifting.
Like the 80-20 rule, but more extreme.
Yeah, think like 10% of the code doing maybe 99% of the actual processing work. And crucially, that heavy work could often be done in parallel.
Ah, so not step by step like a normal CPU.
Exactly.
Yeah.
Not sequential, doing lots of similar things all at once. That insight wasn't just about speed, it was about tackling whole new types of problems.
So the realization was the perfect computer, if you like, needed to be great at both, sequential and parallel.
That's it. It was a totally different way of thinking about computer architecture back then.
Like a radical idea.
Absolutely. And NVIDIA basically said, okay, that's the problem we're going to solve.
Yeah.
Those computational bottlenecks that regular computers just choked on, that was the core idea.
I love that Mythbusters analogy for explaining CPU versus GPU. Remember the paintball robots?
Oh, yeah.
One robot firing one paintball. Bing, 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 bing.
Yeah.
That's your CPU, right? Task after task.
Yeah, sequential.
But then they had that huge rig firing like a wall of paintballs simultaneously.
When? That's a GPU, handling tons of smaller, similar tasks all at the same time.
Perfect picture of it.
It really is. GPUs are just built for that kind of massive parallel work, like calculating the color for millions of pixels on a screen at once for graphics.
Okay, but why games first? Seems a bit niche. Weren't they worried about just being seen as a gaming chip company?
Well, it might look niche now, maybe, but Wang points out a few things. First, games needed that parallel processing for 3D graphics. It wasn't optional.
Okay, makes sense.
Second, he says that they were genuinely passionate about it, about creating these virtual worlds. But third, and this is key, they saw the massive potential growth in entertainment.
Ah, the market size.
Exactly. A huge market meant they could justify a huge R&D budget, which meant better tech, which attracted more game developers, which grew the market.
Which funded more R&D. The positive feedback loop.
You got it.
Yeah.
It was incredibly strategic, not just about passion. That gaming focus built the foundation.
Right, not just chasing a passion project, but using it to build something much bigger.
Precisely. Big market, big R&D budget, better tech, bigger market.
Yeah.
It just kept feeding itself.
It's amazing how focusing on fun essentially laid the groundwork for, well, everything else. You mentioned everything else. I've heard Huang call GPUs time machines. What does he mean by that?
Yeah, the time machine idea. It really captures how speeding up computation lets us, see the future sooner.
How so?
Well, take weather forecasting or climate modeling. Running those complex simulations faster means you get the predictions earlier. Or think about training self-driving cars by simulating virtual cities. You can run millions of miles digitally in a fraction of the real-world time.
So you're fast-forwarding the learning or the prediction process?
Exactly. He tells this really moving story about a quantum chemistry scientist
Oh, yeah.
who realized that because NVIDIA's chips were getting so fast, he could actually complete his entire life's work within his remaining lifetime, something that seemed impossible before.
Wow. That's profound. That really brings it home.
Doesn't it? So this massive speed up, initially driven by games, started opening doors everywhere. And at first, scientists were literally having to, like, trick the GPUs.
Trick them.
Yeah, make their scientific problems look like graphics problems just to access that parallel power.
Okay, that sounds clunky. A workaround, right?
Totally. Which leads us directly to CUDA. That was NVIDIA's answer.
Right, CUDA. The platform to make GPUs easier to program for non-graphic stuff.
Exactly. It lets programmers use languages they already knew, like C, to tap into that GPU power. Lowered the barrier massively.
So what pushed them to create CUDA? Was it just seeing scientists doing these workarounds?
Huang says it was kind of a mix, partly seeing that, yeah, like researchers at Mass General using GPUs for CT scan reconstruction,
Ah, medical imaging.
right? But also internal stuff, wanting to do more complex physics in games like realistic water or explosions, and just fundamentally seeing the huge untapped potential of parallel processing way beyond graphics.
But creating CUDA must have been a massive gamble, right? Betting that scientists and others would actually adopt this whole new way of computing.
Oh, absolutely. A huge bet. But it was calculated. Huang knew the gaming market was making their GPUs the highest volume parallel processors out there. They were everywhere.
So the hardware was already widely distributed?
Exactly. CUDA just made that hardware programmable for everyone else. He calls it an incredibly optimistic, huge if true thing. The belief that if you give people easier access to that much computing power...
They'll invent amazing things with it.
Precisely.
And, well, it seems like that optimism was justified. Which brings us to the AI revolution, and that moment in 2012, AlexNet.
Yeah, 2012. AlexNet wins this big image recognition competition.
Yeah.
Not just wins, but blows the competition away.
And it was a neural network.
A deep neural network trained on tons of data, crucially, using NVIDIA GPUs. It was the proof point. Deep learning, powered by parallel processing, could do things previously thought impossible for AI.
It feels like that was the real paradigm shift, wasn't it? Moving from telling computers exactly what to do step by step.
To showing them examples and letting them learn. Instruction-based versus learning-based computing.
And for NVIDIA, that must have felt like massive validation.
Huge validation. They believed in parallel processing. They'd built CUDA, hoping researchers would find uses. And here it was. Huang even mentioned they'd been struggling internally with computer vision problems themselves, so seeing AlexNet succeed using their hardware.
Must have really hit home. So it wasn't just, oh, cool. It was more like a light bulb moment about the future.
Absolutely. The realization hit. If deep learning can do this for computer vision, what else can it do? The potential seemed limitless. It could reshape the entire computer industry.
And that led to a big internal shift.
Complete overhaul, re-engineering their whole computing stack. Yeah. That's where things like DGX, their dedicated AI supercomputers, came from.
And things just took off after that. Problems that seemed impossible for decades
Suddenly started to fall. Complex computer vision, understanding speech, natural language processing, the progress was incredibly rapid.
It really was. One breakthrough after another, powered by deep learning, big data, and, well, NVIDIA's hardware.
It was a perfect storm, really.
Now, looking back, 2012 feels like the obvious start of this whole AI wave we're in. But for NVIDIA, who'd already bet big years before, what is that decade between AlexNet and now actually like?
It's interesting. Huang sort of says it probably just felt like today. Always challenges, always pushing, always working on the next thing.
Not like they were just waiting for the world to catch up.
No. He stresses how important their core beliefs were. That deep conviction in accelerated computing, in parallel processing, the scalability of neural networks.
Right, they had this foundational belief system driving them.
Exactly. And the belief that AI could learn from all sorts of data. He mentions investing tens of billions of dollars before AI became the huge buzzword it is now.
Wow, tens of billions. That's serious conviction.
It really is. It shows they weren't just reacting. They were actively shaping the future based on those core beliefs. Beliefs that were pretty contrarian for a long time.
And those same core beliefs are still driving their bets today, right? It's not just resting on laurels.
Definitely not. Accelerated computing is still job one. Plus this deep belief in how AI can learn from, as Huang puts it, digital representations of human experience.
Meaning
Text, images, code, sensor data, but also translating between them. Text to image, like we see now, or understanding protein structures from amino acid sequences, or even words translating into robot actions.
that opens up a huge range of problems AI can tackle.
A universe of possibilities, yeah.
So if the last decade was the science of AI, figuring out the fundamentals, what's the next 10 years about?
Huang calls it the application science of AI. It's about taking these powerful tools and actually using them everywhere.
Like where?
Digital biology, climate tech, agriculture, robotics, transportation, education. He even mentioned podcasting. It's about applying AI to solve real problems across the board.
Okay, let's dive into one of those. Physical AI, robotics. That feels like a huge leap, moving from software to things that interact with the real world.
It's a massive focus and, yeah, incredibly exciting. Training robots traditionally is slow, expensive, and risky. You know, robots break, wear out.
Right, and you can only expose them to so many situations in the real world.
Exactly. Or you use things like motion capture, but that's also limited. The game changer is training them in virtual worlds, digital simulations.
The big bang moment for robotics, as he calls it, because you can run simulations way faster and cover way more scenarios.
Exponentially more. And that's where NVIDIA's platforms like Omniverse and Cosmos come in.
Okay, Omniverse, that's the virtual world builder.
Right. Photorealistic 3D worlds for robots to train in safely and quickly.
Yeah.
And Cosmos is newer. It adds this layer of like real world understanding to the simulation.
How does that work? He uses an analogy with ChatGPT.
Yeah, it's a good one. Think about early ChatGPT, amazing at generating text, but sometimes it would just make stuff up, hallucinate.
Okay, yeah.
Then newer models got better because you could give them context, like a PDF or search results, to ground them in facts.
Right, grounding them in reality.
Exactly. So for robots, they need grounding in physical reality. They need what Huang calls a world foundation model.
Like a language model, but for physics and common sense.
Precisely. Understanding gravity, friction, that objects don't just disappear, cause and effect. That's what Cosmos is aiming for.
And Omniverse provides the physics engine, the ground truth for that understanding.
You got it. Omniverse simulates the Newtonian physics. Combine that with Cosmos's common sense understanding, and you can generate basically infinite physically plausible scenarios for robots to learn from.
Wow, so instead of manually programming a factory robot's path?
You simulate millions of variations digitally. Faster, safer, more comprehensive. It completely changes how you train robots.
Which leads to his prediction. Everything that moves will be robotic someday, and it will be soon. That's bold.
Very bold. But he sees robotic lawnmowers, truly autonomous cars, even humanoid robots becoming normal, and soon.
And he even talked about having your own R2-D2, like a personal AI companion.
Yeah, an AI that's integrated into your glasses, your phone, maybe a physical robot, learning and growing with you throughout your life.
That definitely sounds like sci-fi becoming reality.
It does, but he sees it as the logical next step, building on the tech they're developing right now.
Of course, with technology this powerful, people have concerns. Bias, safety. Does he address those?
He does, yeah, directly. Acknowledges the valid worries about bias creeping in from training data, AI saying toxic things, hallucinating, impersonation, and critically, AI safety.
Safety meaning the AI doing the wrong thing.
Right. Making sure the system does what it's supposed to do and doesn't cause harm, even accidentally. He stresses these are huge areas of active research and engineering focus.
He used the self-driving car example, didn't he? The AI wants to drive safely, but what if a sensor fails?
Exactly. It highlights the need for really robust engineering redundancy fail-safes. It's not just about the algorithm being smart. The whole system needs to be safe. He talks about needing a community approach, lots of safeguards.
Okay, what about limits? Are we hitting walls in terms of physics? How much faster can things get?
Ultimately, he says the final limit is energy. How much energy we have and how efficiently we can use it for computation and moving information around.
Yeah.
Physics dictates that.
But we're not there yet.
Not even close, according to him. There's still massive room for improvement.
And he uses their own hardware as proof.
Yeah, the GGX systems. He points out they went from a $250,000 AI supercomputer box in 2016 to a version now that costs around $3,000, but is vastly more powerful and way more energy efficient.
How much more efficient?
He claims a 10,000-fold increase in energy efficiency in just 8 years. 10,000 times.
That's staggering. If cars or light bulbs improved that much.
Right. It shows how much headroom there still is, technologically speaking.
Okay, another interesting point. Designing general-purpose chips versus chips specifically made for, say, the transformer AI models that are dominant now. What's NVIDIA's thinking there?
Their core belief is that AI is still evolving really fast. Transformers are huge now, but they're probably not the final answer. New algorithms, new architectures will keep coming.
So if they build chips only for transformers,
they risk being left behind when the next big thing arrives.
Yeah.
He uses the analogy of turning a computer into just a microwave. it limits future possibilities.
Right, you lose the generality.
Exactly.
Yeah.
And even within transformers, things are changing constantly. Different types of attention, like flash attention, hierarchical attention. The field is moving too fast to lock into one specific design.
So they prioritize flexibility in the hardware.
Flexibility is key. Having an architecture that can accelerate whatever researchers dream up next.
It's also interesting how deep their expertise goes, even though they don't manufacture the chips themselves, right? Like knowing semiconductor physics.
Yeah, even though TSMC makes the chips, NVIDIA has deep internal knowledge of everything from the physics to like the aerodynamics of cooling fans to make them quieter and more efficient.
They need that deep understanding to push the boundaries with their partners.
Exactly. It's about close collaboration and knowing where the physical limits are and how to nudge them.
Which comes back to that theme of making these big, forward-looking bets that seem to keep paying off. So beyond robotics, what are the latest big bets?
Well, combining Omniverse and Cosmos into this generative world generation system is huge, with implications way beyond just robots simulating any complex physical system.
Like what?
Digital biology is a massive one, trying to understand the language of molecules and cells to maybe create digital twins of humans.
For medical breakthroughs?
Potentially revolutionary ones, yeah.
Yeah.
And climate science, high-resolution weather, and climate models to really understand regional impacts.
It all comes back to the time machine idea, doesn't it?
Seeing the future sooner so we can shape it better. That seems to be the driving purpose.
Okay, so for someone listening, trying to figure out how all this impacts them, what's Huang's advice?
He really encourages you to think, what if tasks you do now could be done almost instantly by AI?
Yeah.
How would that change your work?
Like how highways or video conferencing change things?
Exactly. He asks, what if you had an expert software programmer on call, 24/7, or a rapid prototyping tool? What new things could you create? What opportunities open up?
He also makes that prediction about superhuman intelligence.
Yeah, that AI will become superhuman in some areas within the next decade. Which sounds intimidating, maybe.
Little.
But he frames it positively based on his experience working with brilliant people. It's empowering, not diminishing. His main advice.
What is it?
Go get yourself an AI tutor right away. Use ChatGPT, Gemini Pro, Grok. Start playing with them now.
So step one is just dive in, learn to interact with these tools.
Absolutely. Learn how to prompt them effectively. He says it's like learning to ask good questions.
And keep asking yourself.
How can I use AI to do my job better? He sees it as essential, like learning to use a computer was for previous generations.
Does he think it's hard to learn?
Actually, the opposite. He argues AI is making tech more accessible, lowering barriers. Think how easy ChatGPT is to pick up compared to, say, learning complex software from scratch. The message is optimistic. AI augments us, makes us superhuman.
To make it concrete, he showed off the new GeForce RTX 50 series card, calling it a supercomputer in your PC.
Right, highlighting its power not just for gaming or design, but for AI too. He talked about AI-powered graphics.
How does that work?
Essentially, AI predicts most of the pixels on a 4K screen based on a much smaller number of actually computed pixels. It looks perfect, but frees up massive computing power for even better quality or performance.
Another example of AI freeing up resources.
Exactly. And then he showed the smaller, cheaper AI supercomputer.
The $3,000 one down from $250,000.
Yeah, making that kind of power accessible to way more engineers, students, researchers. His hope is enabling everyone to build your own AI, build your own R2-D2, democratizing it.
So that final advice really hammers home the need to learn AI interaction.
It does. Learn prompting, learn how to work with AI, whatever your job is.
Yeah.
Asking AI to be your assistant is a skill, an art even. And keep asking that core question, how can I use AI to do my job better?
And looking back at his own work, what does he hope people remember? What's the theme?
His answer was simple. They made an extraordinary impact.
And he links that impact back to those core beliefs they held for so long.
Yes, and the sense of responsibility that comes with being so influential now. He stresses their commitment to making their tech available to everyone, big companies, small startups, researchers.
His hopes for the future sound huge.
Transforming biology, materials science, robotics taking over dangerous jobs, self-driving cars giving us back time.
Yeah.
And NVIDIA being seen as central to all that.
Not just the company you played games on.
Exactly. A foundational technology provider for this next era.
Wow. Okay, so wrapping this up, this deep dive really shows this accelerating wave powered by parallel processing and AI. It's a story of insights, big bets, and this shift from just figuring out AI to actually applying it everywhere.
Absolutely. And for you listening, Really take Huang's advice. Think about how near-instant task completion could change your work. What possibilities open up when intelligence is this accessible?
So the call to action is experiment.
Yeah, start using the tools. Ask yourself how AI can make you better at what you do. Think about the future that's unfolding right now and, what your part in it could be. What opportunities, maybe even challenges does it create for you personally?